So in this video, we're going to look at the integrals of logarithmic functions. So the integral of ln of u du is equal to u times the ln of u minus 1 in brackets plus c. And if our base is something other than e, Euler's number, so b, where b is positive and not equal to 1, then log base b of u du is equal to that same u times bracket ln of u minus 1 over the ln of b plus the integration constant c. So let's look at some examples. First example we're going to look at is the integral of 4 times log base 2 of x dx. So the first thing we can do is think of that 4 as being a constant multiplier. So this would be 4 times the integral of log base 2 of x dx. And there's nothing complicating the integral here. This is an integral, the form log base b of x, where b is equal to 2. So our integral then will be 4 times u, which in this case is x, times the ln of x minus 1, all divided by the ln of our base 2 plus c. And if we wanted to, we could write that as a single fraction. So 4x ln of x minus 1, that should all be in brackets, divided by ln of 2 plus c. And that would be our final answer. So let's look at another one. So now we're looking at the integral of ln of 2x minus 3. So we don't have just an x that we're taking the ln of, now we're taking the ln logarithm of two terms, the 2x minus 3. So this is a situation where we're going to have to use substitution. So we'll let u, there we go, equal 2x minus 3. And then taking the derivative of that, du by dx, we get 2. And then rearranging, we get du equals 2 dx, or du over 2 equals dx. So then substituting, we have the integral of the ln of u times, and then in place of dx, we have du over 2. So again, we used u to replace 2x minus 3, took the derivative of that, which was 2, then rearranged that derivative to isolate the dx, so dx is equal to du over 2, then replaced the 2x minus 3 with u, and the dx with du over 2. And we could also write this as 1/2 integral of ln of u du. So now, integrating, we have 1/2 times the integral of ln of u is u times the ln of u minus 1 in brackets, plus our integration constant c. And now we'll replace the u with our original 2x minus 3, so we have to replace that in both of the u's. So we'll have 1/2 times, in brackets, because u now is multiple terms, 2x minus 3. And then I'm going to use square brackets for this, just to distinguish ln of, again, u, which is 2x minus 3, minus 1, plus c. So we could also write this as a single fraction. So 2x minus 3 times the ln of 2x minus 3 minus 1 in brackets over 2 plus c. And that would be our final answer. If we wanted to, we could do some multiplication. We could take the 2x minus 3 and multiply by the negative 1, divide by 2, and then combine with the c. But for me, I would leave this just how it is. Unless we could divide the 2x minus 3 by the 2 right now, but the 3 isn't divisible by 2, so I would just leave this how it is. So let's look at another example. Now we have log of 9x. And I'm going to look at two ways that we could approach this one. First one I'll look at is using substitution. So I'll just split down the screen here to look at our two methods. So the first one would be using substitution, so letting u equal 9x, taking the derivative of that, du by dx is equal to 9, so then du equals 9 dx, or du over 9 is equal to dx. So then our integral of log of 9x dx becomes the integral of log of u times du over 9. So we have 1 over 9 integral log of u du. So then taking the integral, this is log, and because the base isn't specified, that means it's log base 10, the common logarithm. So we'd have 1 over 9 times ln 10 in the denominator, u times bracket ln of u minus 1 plus c. So we'd end up with 1 over 9 times 9x times ln of 9x minus 1 all over the ln of 10 plus c. Now this is a case where this 9 out in front that's dividing could divide out this 9. And if we do that, then we end up with x times ln of 9x minus 1 all over ln of 10 plus c. So that would be our final answer. So that's one way that we can approach it. The other way to approach it would be to use our properties of logarithms. So to take that log of 9x and break it apart to say that this is the integral of log of 9 plus log of x dx. Now, the one benefit to doing this is we don't have to use substitution. This log of 9, that's just a constant. That is just like having a 5 there. So when we take the integral of that log of 9, it turns into just log of 9 times x. And the integral of log of x, so we'd have plus log of x, plus the integral of log of x, would be x ln x minus 1 in brackets divided by the ln of 10 plus c. So our final answer would be, and usually I would write this in this way, x log 9 plus x times the ln of x minus 1 over the ln of 10 plus c. So these two answers look quite different, but if we were to go through the properties of logarithms, we'd be able to show that these two are actually equivalent to each other. So even though they look quite different, they are equal to each other. We would just have to use the properties of logarithms to work our way through to get there. So now let's look at the integral of x ln x squared plus 7. So we have now an x that's multiplying out in front. That's complicating matters. We also have two terms inside of the logarithm, which, as we saw before, means that we really need to use substitution. We have the rule for the integral of ln of u, so we need to get into that form. So we'll start with the substitution. So letting u equal x squared plus 7, then taking the derivative, so du by dx is equal to 2x, so then du is equal to 2x dx. And then this is where we can look at that x times ln of x squared plus 7 dx. And we can think of that, we can treat this or look at this in a couple of different ways. One way is to say, well, this is ln of x squared plus 7 times x dx. And then noticing this x dx is the same as this x dx. So if we divided both sides of this by 2, we'd have du over 2 equals x dx. And then we could make that substitution. We could say, well, x times dx by this is equal to du over 2. So we could say that this is the integral of ln of u times du over 2. So then that 2 comes out in front, times the integral of ln of u du. Then integrating, we get 1/2 times the u times bracket ln of u minus 1, all plus c. And then substituting in for u, the x squared plus 7, we have 1/2 x squared plus 7 times bracket ln of x squared plus 7, close off that bracket, minus 1, close off that one, plus c. And that would be our final answer. We could write that all over 2, but I wouldn't bother. I would probably just leave it in this form. The other way that we could have approached this would be to, instead of writing the du over 2 equals x dx, we could have said, well, du over 2x is equal to dx, and then made the substitution and said, well, we have integral of x ln of u times du over 2x. So coming down from here to here. So keeping the x there, replacing the x squared plus 7 with u, and the dx with du over 2x. The x cancels out, so we end up with the same 1 over 2 times the integral of ln of u du. So we end up at the same place. It's just a different way of looking at the substitution. Either way gets you to the same final answer. So either way is acceptable. It's kind of a personal preference. That said, some mathematicians would not appreciate this approach. For me, I have no problem with it as long as when you integrate, and this is the important part, when you integrate, you have to make sure that at this step where we're going to then integrate, we only have one variable. So we just have a u variable. There's no mixture of x's and u's. So just make sure if you use this approach, no matter how you integrate, you should have at most one variable. So there shouldn't be a mixture of x's and u's. It should either be all x's, all u's, never a mixture. Let's look at another example. So now let's look at the integral of ln of x squared. So in the previous one we had x times the ln of x squared plus 7. Now we have just ln of x squared. This is one where if we were to try to do a substitution, we would run into some problems. So if we said, well, let's let u equal x squared, then du by dx would equal 2x. So du equals 2x dx. Well, the problem is we don't have an x in our integral to pair off with a dx to get this. And even if we were to do this rearranging and say, well, let's let du over 2x equal dx and substitute that in, we'd have ln of u times du over 2x. That's a problem. That's a problem because now we have a mixture of variables. We have a u and we have an x. We can't do anything with that. If we have a mixture of variables, we are in trouble. So the substitution, we can't use that. There's nothing that we can do to substitute because this x will always be there from the derivative. So instead, well, we just go to our properties for logarithms and say, well, ln of x squared dx, if we use the properties of logarithms, that's equal to 2 times the ln of x dx. So using the properties of logarithms, which says that if you have ln of x squared, we can bring this exponent down and write this as the integral of 2 ln x dx. Well, this isn't a problem now at all, because this is just 2 times the integral of ln of x dx, which we can integrate just using the rule. So that would be 2 times u, which in this case is x, times bracket ln of u, so ln of x minus 1, plus c. So we end up with 2x times ln of x minus 1 plus c. That would be our final answer. So just keep that in mind when you're taking the integral of logarithmic functions, that in some cases we can just use the properties of logarithms to simplify matters for us. So in this case, we could use the properties of logarithms to say, well, ln of x squared is the same as 2 ln x, and then just take the integral. In the previous example where we had ln of x squared plus 7, the fact that we had a plus 7 there, we had 2 terms inside of the logarithm, that prevented us from using our properties, because the ln of x squared plus 7 is just the ln of x squared plus 7. There's nothing that can be done about that. There are no properties that allow us to simplify that. That plus 7 keeps us from taking the 2 out in front. So for the previous example, that was all we could do. We couldn't use the properties, but for this one, we could. So now let's look at the log, or the integral of log of 3 root x dx. So for this one, again, if we tried to use substitution, we would run into trouble, because if we let u equal 3 root x, we would end up with, well, let's write that first as fractional exponent. If we took the derivative, we would end up with 3 times 1/2 x to the negative 1/2. So we'd have du over dx equals 3 over 2 root x. So just taking that x to the negative 1/2, throwing it in the denominator and writing it as a root. So that would give us then, well, if we rearrange this, du equals 3 over 2 root x dx, which is a problem because, again, we don't have a root x in our in our integral to deal with this root x in our derivative. So we could try making this substitution, but we wouldn't be able to get anywhere because we would end up with a mixture of u's and x's, or u's and root x's in this case. So that approach won't work. There are ways to do that, but we're talking about higher level, more complicated integration methods to be able to do that. So we need to find a different approach. And that different approach is to say, well, okay, we can't go this way, so let's try to use our properties. So the properties of logarithms say that when we have a multiplication of 2 terms, like we have here, so the 3 times root x, we can write that as separate logarithms. So we can write that as log of 3 plus the log of root x. So now, well, we can take the integral of that log of 3. That's just a constant, kind of like that previous example I looked at where we took the 9x and split it apart. So this is no longer a problem. We can take the integral of that. The log of square root of x, well, that's still a problem, but we can also say, well, this is the log of x to the 1/2. And then kind of like in the previous example, we can take that 1/2 out in front of that logarithm to say that this is the logarithm of, or log 3 plus 1/2 log of x. And now we can take the integral of these terms. We can't bring the 1/2 out in front completely, because of this log of 3. So because we have two parts to this, the log 3 and the log x, we can't take this 2 out in front, so we just have to keep it paired with the log of x. So integrating, we get the integral of log of 3. Log of 3 again is just a constant, so we'll have log of 3 times x plus 1/2 times the integral of log of x is x bracket ln of x minus 1 plus our constant c. So we end up with, and again, usually we would write the x out in front of the logarithm just so it doesn't get confused as being part of the logarithm. So x log 3, then plus 1/2 of x times the ln of x minus 1 plus c, and that would be our final answer.